Significant figures are important in science. It is based on the measuring tools that you're using to take the measurements, because in science, that's what we do. We do laboratory experiments where we take measurements. And looking at these two rulers for this example, what do you see here that's a little bit different about ruler A and ruler B in comparing the two together? Decimal places, yes, or tick marks. Okay, so looking here where this one goes by the ones and this one goes by the tenths in terms of the calibration of the measuring tool. Which one do you think is the better measuring tool then? Yes, definitely B. It has more precision marks on it, and that's going to give you a better measurement. So comparing A up here, where you draw the line and all you get to do, it's definitely for something because you're right here on this tick mark, but you have to estimate the second digit here, and it's a guess. It's an uncertain digit, and it's one that's going to be estimated. But if you're looking here, the best estimate I got was 9. I guess you could have gone with 4.8 as well. If you look at ruler B though, you do get the 4 and then you get the 8 by its tick mark here, and then you estimate one more digit. And I gave it a 7, although like I would accept 488 too. I think that would be a reasonable estimation for that particular measurement. What we're trying to get at here is that ruler A provides you two significant figures. You only get, one actual absolute digit, and then the second one, the 9 here, or the 8, would be the uncertain digits. You only get 2 digits in your measurement. Whereas ruler B is going to give you 3 significant figures or digits because the precision of the measuring tool is better and it's better calibrated. So you get to go out to the hundredths here and get a better measurement. Sort of an introduction here to significant figures. The learning targets for significant figures. You can determine the number of significant figures or digits in a measurement. We use it back and forth. Some years they're like, we want to call them significant figures. Other years we want to call them significant digits. So you can say sig figs or sig digs. It really doesn't matter. And you're going to be able to express your answers from calculations with the correct number of significant figures / digits, whichever way you want to call them. As the example with the rulers, this one's an example with the graduated cylinders. Representation of the number of digits in a measurement that includes all the numbers that you are absolutely sure of, plus one estimated number, and that's called the uncertainty of the measurement there. This is an indication of the precision of your measurement here. Now we're going to practice a little bit with some graduated cylinders because we do lots of volume measurements in chemistry, but I just want to point out that you always measure with the graduated cylinder from the bottom of the meniscus, that curve of the liquid there. So if I was looking at this particular one, where I kind of drew over the line here, so I'm going to erase that part. But if I was going to look at this one and estimate, this is definitely going by ones. So first thing, look at, how is your tool measured? Like what's the calibration marks on it? This is 30, so that's 35, that's 36. So far I got 36. Now I have to look at where I think the bottom of that meniscus is. I think it's slightly above center. So you could, I would estimate it as, 36.6 milliliters, or 36.7 milliliters would also be, I would think would be a reasonable estimate as for that particular last digit. Now I want you to do some practice. Try out these graduated cylinders. Looking at the first graduated cylinder to the left there, what is the calibration markings on it? Let's go to the ones, the tenths, the hundredths. Yes, it's definitely to the tenths. So when we're measuring, that means my measurement has to go to the hundredths because it goes one past the tick mark or the calibration mark on the measuring tool. So looking here, it's definitely 2, this is 5, 6, so this has got to be, 2.6. What are you estimating the bottom of that meniscus as? It's definitely not on the line. It looks more towards the middle. Is it above the center, below the center, right at the center? What do you think? 6, 7, a little bit above center. Okay. Anybody else? Yes, I think it looks pretty much at center too. So, but I would accept these estimations. I thought 2.65 myself. So, but 2.67 is okay and would be accepted. How about the second graduated cylinder? What does this one go by? Definitely goes by ones. That means my estimation is going to go to the tenths. So here we have, here's the 35, 36. What do you think? In the middle, above the middle, below the middle? All right, definitely 8 looks good, 7 looks good. I think those are both reasonable estimations. I put a 7, but the 8 is still good. The third graduated cylinder, what are we looking at here? Ones, tenths, hundredths, what? So here's the 20 mark. Here's the 30 mark. Yeah, okay, good. We got the ones now. All right, ones definitely. Now go up here, this is the 25 mark, so it's between 25 and 26, so we're at 25. What estimate would you give that one? I definitely think it's closer. Yes, I think I went with the 8, but yep, I went with the 8, but a 7 would be accepted there as well. Last graduated cylinder, how is this one calibrated? We have our 5, we have our 6. So this one goes to this is the tenths, yes. So each little tick mark is worth a tenth. And this bottom of the meniscus seems very close to me. So this would be 5.4, and then 9 looks good to me. I agree. 9 sounds good, or 8. But you would only estimate out 1 past the tenths. So since this is to the tenths, you would only give 1 more digit, which would be the estimated digit to the hundredths. You wouldn't want to go out any farther. I do want to point out one other thing about measuring with graduated cylinders, or even a ruler of sort. If the bottom of the meniscus actually does land on a line, say it was right here and it was exactly on this line for this particular one. What you do in that situation, because you do have to keep the digit to the hundredths, I would say it's 5.2, but then what you put in for this measurement part, saying it fell on the line, is a 0. But you have to still have the 2 digits to the right. You have to have all 3, because you're saying that the meniscus is directly on the line. That's the only weird case, I would say, when it comes to measuring. So looking at the ruler measuring tools, we're going to compare measuring this insect with 3 differently calibrated rulers. Looking at the first one here, the first one, has very little markings. The middle one has few markings, and then this one over here to the right, the C one, has a ton of markings. The more markings there are, the better the precision of the measuring tool. And when you measure, you're estimating 1 place value past the markings of the measuring tool. So looking at A here, what could we estimate our insect at? It's just one big, no markings in between. So how many digits really can we give this? Yeah, just the 1. You get to estimate, like halfway is about right here. So a little bit above halfway. Yes, 0.6 seems reasonable for A. Okay, so far so good. Let's look at B now. B has other markings, so it's 0 to 1. These markings represent tenths. So now we know this is a 6, and we can estimate 1 past the 6. And what would you think would be a good measurement for B? Yes, very good. 6'3", 6'2", looks good to me. The last one's harder to tell because you can't really see the tick marks very well, but these are broken up. Here's your centimeter. So like that is like 5 millimeters. This is like 5 millimeters. And it's really hard to tell in there. Not milliliters, millimeters. This whole thing right here ends up being, you know, from the centimeter, we know there's 10 millimeters in a centimeter, if you remember metrics. So this one is calibrated out to the hundredths. So the centimeters, which would be the estimating here in between the centimeter. Now we're going to try to estimate between the millimeter here. So we would add one more digit. I know it's really hard to see, but looking here, we're going to give it the, you know, oh, that should be more like a 3, I think. Should be more like a 3. We go up because this is the centimeter, the 6, then go up here and be able to see that it's about 3 up. Okay. Basically, though, the gist of measuring this insect is telling us there's different significant figures based off of the measuring tools. So A only has one measuring tool, has only one tick mark, so it only has one significant figure. B has 2 significant figures because of the calibration, and then C over here is going to have 3 significant figures. So out of these measuring tools, which one would be the best one to use? Yes, definitely C. Now, determining significant figures in a measurement is a skill that you have to become pretty good at, and you need it for physics, you need it for AP Chem if you choose to take AP Chem. So we're going to try to hopefully solidify this now. There's a couple different ways you can learn the rules. You can memorize them, of course, or you can try the Atlantic Pacific rule. And it's based off of the, you know, where the Atlantic and Pacific Oceans are in the United States. So over here in the West Coast, which oceans over here? Anybody have good geography skills? What's going to be over here, this ocean? That's the Pacific. Good. So the Pacific's over on the left side if you're looking at a map of the United States. We say Pacific Ocean has a decimal point. It has to have a decimal point in the number. And you start counting from the left. So for example, if it has a decimal point, you start counting from the first non-zero digit, that's 1 through 9. Everything after that first non-zero digit counts as a significant figure based off of the measuring tool. How many significant figures would be in this measurement of grams? So we count the 1, that's the first non-zero. Now everything after it counts. So yes, it would be 5. This one would have 5 significant digits in it. So using the Pacific rule, you start from the left. You use your arrow or your mental arrow to find the first non-zero digit, and then everything after that counts. Doesn't matter if it's 0 or a 1 through 9 number. On the Atlantic side, we say absent, like the decimal point is absent. There is no decimal point. You're going to start counting from the right. For example, in this measurement, this 2,500 grams. So we're going to start from the right now because there is no decimal point in this number. We go to the first non-zero digit, which happens to be the 5. That's the first one. Everything after that now counts as a significant digit. So how many significant digits would this one have? Definitely 6. Good. Now we're going to take a look at the rules. You can look at it from the rule standpoint. You could use this strategy or you can memorize the rules. Non-zero numbers are always significant, and we're saying non-zero 1 through 9. Whenever you see any of those, they count. They're automatically significant. So, examples here. How many significant digits in the 72.356 then? Always significant. How many sig figs in this one? Yes, 5 is correct, because all of them are non-zero digits, so they automatically count. How about this example, the 7,874.12? All of them are non-zero, so they all count. So there is 6 significant digits there. Second rule, zeros between non-zero numbers are always significant. So if the zero is between a 1 and a 9 type number, it's going to count as a significant figure. So that's where we say between. These two zeros are between the 8 and the 2 here. All right? That's what we're talking about being between. How many significant figures for this example right here? Good, 5, got that. How about the 60.5? 3. Excellent. So far, so good. Those are the easier rules. Let's take a look at the not so easy rules. All final zeros to the right of the decimal place are significant. So we're talking about, say you have this number here and then you have a 0 to the right. So this is the one that they're talking about, the final zeros added on. Those zeros, when they're going past a non-zero digit, they count, they are significant. How many significant figures in this example? Correct, 5, very good. This example right here, you have 2 zeros that have been tacked on as final zeros. How many there? 5 also, very good. Now, this is the hardest to recognize, the zeros that act as placeholders. They are placeholders, they're holding place values. They're not between non-zero digits. These ones are just placeholders and they are not significant. So looking here at our example here, these zeros before the non-zero digit starts, these are the placeholder zeros I'm talking about. So they would not be significant. I also could use the Pacific rule, start from the left, go to the first non-zero digit, which happens to be the 1. Now everything after that counts. So how many digits for this particular example? That one only has 3. That is correct. Now looking here at this one with all these placeholder zeros, I just kind of draw my line through them. How many digits? 2. Good. On the other side, where we do not have numbers that have decimal points in them, this 4,210, this is like the Atlantic rule. Now I'm going to start from the right because the decimal point is absent. Go this way. This 0 is considered a placeholder. So I go this way. My first non-zero is the 1. Now everything will count. How many are in that particular number? Good, 3. And the 189,000, once again, you have 3 placeholder zeros. Those ones would not be considered significant. So how many for that example? Correct, 3. So now we have a practice table. I'm going to let you have a couple minutes to do some of these before we start calculating with our significant figures. Looking here, starting with our number 3. I think that one's pretty obvious, but how many significant figures would that one have? Yes, it's pretty obvious. It would be 1. Now looking at our second example, you can tell me decimal point, first non-zero, everything after it counts. That one has 7. Very good. How about the 9,009? 4 is correct. These zeros are in between, so they definitely are significant. How about 45.00? Yes, 4. Very good. You start from the left. First non-zero, everything after it counts. Those trailing zeros now count. 9.01. Definitely 3. That zero's in between, that counts. How about this 0.00068? Good. 2. Once again, draw it through. There you go. And 0.0880. 3. These are placeholders. They don't count. Very good. Over here, this, how much is that? 71 million. Start from the right. This is the Atlantic or absent. Good. 2. 0.2. Just the 1. Good. How about 910.0? Good. All 4 count. Just about how 910. Yeah, that one's from the right this time. So there's only 2. Good. 90. Yes, only 1 for that one. And 0.009. You guys are definitely getting the hang of it now. That's great. And last but not least. Yes, so this one's going to have 2. Easy part so far, identify the number of significant figures or digits. Now we got to do some math with it. I hope you have your calculator out because you definitely don't want to do this mental math. Addition and subtraction. They have their own rule, addition and subtraction. They can have only as many decimal places as the fewest number of decimal places in the starting numbers. So you're really looking for place value here. I like to think about it like this. Like so. Okay, so out of all of these numbers, the 1 has the least amount of precision, whereas the 9 has the most amount of precision. You get more precise as you go this way. So you're looking for the precision in the place value because that's based off the measuring tool that you use, the specific ruler or graduated cylinder or burette or whatever. So looking at number of decimal places, and you're going to round your answer to that least amount of decimal places. Multiplication and division, different rule though. You're looking for the fewest number of significant digits in the original measurements. Your answer is only as good as the amount of digits in your original measurement, basically. So if you have a number that's, say you're multiplying 1.0 times 450.0. Well, this one has 2 significant figures. This one has 4. So guess what? My answer is only allowed to have 2 significant figures because of this measurement over here is limiting the amount that I can have in my final answer. Let's do some examples. First one's addition, subtraction. This one, find the mean. Oh, find the mean here. So we need to add these up. We first need to do the math. Everybody needs to do the math. All right, so go ahead, take a moment and add those up. And we get this 7.31. Now, to find the mean, we need to divide by 4 because there's 4 values here, right? Divide that by 4. And we end up with 1.8275 or something like that. Now the 4, because it's a mean, that's not considered a significant figure or anything. We're going to base it off of what we originally had here because we had to do the adding up here. So we have a tenth, we have a hundredth, we have a thousandth, and we have a tenth. How many digits can my answer go out? Which place value? Which one's the least precise? The tenth. So this is where we're going to round to. Now, looking to the right of the 8 there, is that a 5 or above? No. So we're just going to leave it as 1.8. Does that make sense? This would be your final answer. Now let's do an example, and I threw in the density. Everybody remember the density equation? Woohoo! Mass over volume. Hopefully you remember that's coming back to you now. I put the little triangle here too, the DMV. But we have a mass of 10.51 2.1 grams, we have a volume of 2.1 milliliters. So yeah, we're just going to divide the mass by the volume to get our density, which is fine. And go ahead and do the calculator answer, because it's always easier to start there. So I'm getting 5.00476, blah, 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 right? Don't need all those digits. Now what I have to consider is my measurements here. How many digits are in the 10.51? 4, good. How many digits are in my volume over here, the 2.1? Only 2. So guess how many digits my answer can have? Yes, only 2. Now, the way to round those is you start from the left. You keep the 5, you look to the 0 here. Now, to the right of this 0 is another 0. If it is, 5 or above, I would round up, but since this is, 4 or below, I'm not going to round up. It's just going to end up being 5.0 grams per milliliter. All right, looking up here. This is an addition problem. We're following the addition rules. So when you added those up, what did you get for your calculator or original answer? Yes, that's correct. Very good. So that's what should have popped up on your calculator screen. Now we have to examine our original numbers. This one goes to the tenths, this one goes to the tenths, this one goes to the hundredths. So where do I round my answer to? Yes, to the tenths is where I'm going to round it. So this is, because this is a 2 here, I'm not going to round it up. I'm going to leave it a 9. Second example is a subtraction problem. What is the calculator answer for that? Correct. Good. Now, in this case, we have the ones and we have the hundredths. So no decimal places to 2 decimal places. Where are we going to round? To the 1. So this 3 is where we're rounding. I look to this 8. Am I going to round it up or leave it a 3? Round up. So the 8 rounds up to 3, and I get 214 is correct. Looking here at the 50 times the 7.2, what is the calculator answer? 360, very good. Now we have to count the number of sig figs in our original measurements. In 50, how many significant figures does this number have? Only 1, very good. 7.2 has how many digits? 2, good. So how many can I have in my answer then? Yes, only 1. So this is the 3, I have to look to the 3. Next to the 3 is a 6. Do I round it up to a 4 or leave it a 3? Does it stay at 3 or does it go up? It goes up. So I round this up. That means this spot where the 6 was becomes a filler 0. It becomes filler 0 right here. A non-significant placeholder. Understand that. That one's kind of a tricky one. Down here for dividing, what is our calculator answer? Who did that division and has the calculator answer? Anyone? Anyone? Hey, okay, good. Let's go for digits now. How many digits here? In our 60.2. That's 3. How many digits in this one? That's going to be 4. So how many does my answer get to have? Hopefully somebody said only 3. I can't really see the chat anymore, but it started going so fast. So I keep my 2, I keep my 9. This is the 9 I looked for rounding. Do I round it up or leave it a 9? Leave it a 9. Very good. So it's 2.99 is the final answer there. Going back to the other set of notes, the mass, average atomic mass and isotope ones. Now we're going to define a few things